Welcome to this video introduction to thromboelastography. In this video, we will explore what thromboelastography is, how it works, and its application in measuring patients' blood coagulability. Thromboelastography, the abbreviation of which is TEG, is first described by Dr. Helmut Hartert, who was working at the University of Heidelberg in Germany in 1948. TEG is often also called a blood viscoelastic assay. This non-invasive test assesses the entire process of clot formation and dissolution by measuring the viscosity and elasticity of a whole blood sample during clotting under low shear stress. The first reported clinical use of TEG was to guide blood component therapy for wounded soldiers during the Vietnam War. Gradually, studies and practice show that TEG was useful for patients undergoing liver transplant and to monitor patients during cardiac surgery. Demonstrations of the clinical utility of TEG have grown in the past few decades, and TEG devices are now used as a point-of-care test in hospitals around the world to assess coagulation and which components of the hemostatic system are impaired to guide transfusion. The TEG instrument consists of two chambers simultaneously examining a blood sample in duplicate to reduce the risk of sampling and measurement errors. Each chamber consists of a cup slot that can automatically adjust the constant temperature set at 37 degrees Celsius, a freely rotatable stainless steel hanging wire filament, a metal pin, and an electromechanical transducer. After placing the test cup and lid into the cup slot, the metal probe under the suspended wire connected to the sensor enters the lid. Under simulated human body temperature conditions of 37 degrees Celsius, the processed blood specimen is added to the test cup. The cup oscillates around the detection pin at an angle of 4 degrees 45 and a speed of 1 revolution every 9 to 10 seconds under the drive of the cup slot to simulate blood flow velocity in human blood vessels. When the blood is in a liquid state, the rotation of the test cup does not affect the lid and metal pin. As the blood coagulates, it begins to adhere to both the lid and the pin, and movement of the cup induces motion on the pin. These gradually increasing viscoelastic mechanical properties of the blood reflect the developing three-dimensional fibrin mesh and platelet components of the clot. The greater the viscoelasticity of the clot, the higher the amplitude of the pin motion. As fibrinolysis starts, the fibrin platelet structure begins to dissolve gradually, and the clot loses its contact with the detection pin, which has less induced motion. The thromboelastogram is a graphical image of the recorded amplitude of movement of the pin as a function of time. Analytical software measures and quantifies these changes. Therefore, TEG measures the functional ability of the blood to make a hemostatic plug. The detection of TEG can be mainly divided into 5 types: the standard cup detection, or TEG, activated coagulation detection, or rapid TEG, heparinase comparison detection, or heparinase cup, or HTEG, functional fibrinogen detection, or functional fibrinogen, and platelet mapping testing, or platelet cup. Different methods use different activators and have different main functions. Today, let's first learn about 2 TEG methods: standard TEG and rapid TEG. First is standard TEG. It takes 30 to 40 minutes, or maybe a little bit faster. You add calcium chloride, and so calcium chloride counteracts citrate. It's important that when these blood samples are drawn in a citrated tube so it doesn't coagulate. You're also going to add in what's called callin. Callin is a silica and it simulates cell surfaces, which activates the intrinsic coagulation cascade. In addition, phospholipids are added, which are important cofactors in coagulation. In the rapid TEG, this is a little bit different. We're going to add calcium chloride if we're using citrated blood. We're going to add in those phospholipids and tissue factor. Tissue factor activates the extrinsic coagulation cascade, which is a little faster than the intrinsic coagulation cascade, which leads to more rapid results. So the rapid TEG is going to take about only 15 minutes, and that's why it can be so helpful when you're using it to guide blood product administration in a trauma resuscitation where you really can't wait that full 30 to 45 minutes. Now, let's look at the thromboelastogram. It's easy to divide it into 2 segments: The first segment is the coagulation, or the formation of the clot. The second segment is the breakdown of the clot, or fibrinolysis. The first thing to look at is the R time. R time is the time of latency from start of test to initial fibrin formation. It is dependent on the presence of coagulation factors within the blood and the ability of the blood to generate thrombin. Coagulation factors are essentially enzymes that drive clot formation. A normal R time is typically 5 to 10 minutes. If we don't have enough coagulation factors in the blood, or we're inhibiting them with heparin, then R time is going to be prolonged. If we have too many coagulation factors or we're overcoagulating, then the R time might be shortened. Next, we move on to the kinetic time, or K time. The K time is a measurement of clot strength and is indicative of clot strength as fibrin deposition and platelet cross-linking are happening. As the clot gets increased in strength, the time it takes to go from the end of the R time to 20 millimeters across the waveform is known as the K time. The K time is clinically related to the amount of fibrinogen and also platelet number present within the blood. The alpha angle here is a little different. It's not a time, but it's a measurement of the slope of the waveform. The angle increases as clot formation occurs faster and decreases as clot formation takes more time. A normal alpha angle is between 53 and 72 degrees and is related to the amount of fibrinogen as well as platelet number present within the blood. Let's move on to the maximum amplitude, the abbreviation of which is MA. This is the widest distance between the two lines in the waveform, so this is indicative of both platelet number and platelet function. Normal maximum amplitude is between 50 and 70 millimeters. The last parameter is related to clot dissolution, or fibrinolysis, which occurs in the second half of the waveform. This parameter is called the LY30, or lysis at 30 minutes. LY30 measures the percentage decrease in amplitude 30 minutes post-MA and gives a measure of degree of fibrinolysis. Unlike conventional coagulation function tests such as PT, APTT, etc., TEG can reflect the interaction between platelets and coagulation factors during the coagulation process, showing the entire process of coagulation occurrence and development. It can analyze the functional levels of each component in the continuous process, from the activation of coagulation factors to stable platelet fibrin clot formations, and then to the final fibrinolysis. This test requires less blood and does not require special treatment. Whole blood, plasma, and platelet-rich plasma can be used for testing. Another method that detects blood coagulation through viscoelastic measurement, like TEG, is rotational thromboelastometry, or ROTEM for short. It is an improved TEG. The test is made simpler by the automation of the analytical processes. The sensitivity to agitation is also minimized, which allows the device to be used in a broader range of clinical settings. In the ROTEM system, a cylindrical cup containing 340 microliters of whole blood, 300 microliters of whole blood, 20 microliters of CaCl2, and 20 microliters of an activator remains fixed, while a pin suspended on a ball-bearing mechanism initially oscillates through 4 degrees 75 every 6 seconds through the application of a constant force. As the viscoelastic strength of the clot increases, the rotation of the pin is impeded and is detected optically using a charge-coupled device image sensor system. So TEG rotates the cup, and ROTEM rotates the pin. Another advantage of ROTEM is that a standard ROTEM device is capable of analyzing 4 samples simultaneously, as opposed to a TEG device, which is only capable of analyzing 2 samples simultaneously. After discussing above, we know that TEG is a very important test that gives doctors a global assessment of patients' blood coagulability in a fast speed, while other coagulation tests including platelet count, prothrombin time (PT), activated partial thromboplastin time (APTT) give partial pictures of blood coagulability. Now it is widely used in the management of perioperative bleeding in areas such as cardiovascular surgery, orthotropic liver transplantation, postpartum hemorrhage, spinal surgery, and trauma. Thank you for watching.